Let's talk about section 5.3, Poisson's distribution. Now with Poisson's distribution, it is a discrete probability distribution for the number of possible successes over a given interval of time. Remind yourself of the word discrete. It means that we're looking at a variable that is a countable variable. It's discrete in the meaning of how we can count it. The Poisson distribution does have a couple of properties in order for it to be considered Poisson. Remember that each success must be independent of each other. The Poisson distribution, that random variable x, is going to count the number of successes in a given interval itself. The mean number of successes in a given interval must remain constant. And for Poisson distribution, the mean and the variance are given basically as our mean is our standard deviation squared, which is called lambda, where lambda is the mean number of successes in the given interval itself. Okay, so again, if you kind of remember when we saw that lowercase sigma squared, which is that kind of funky looking r squared, that funky looking r by itself without the power of 2 is our standard deviation. But when you square it, it became the variance. So basically our variance is our mean, also known as the lambda in this case here. Okay. Another thing that you want to kind of just remind yourself is that e to the x, or e of x, is our mean. For the random variable for x, we learned this back in an earlier section. So that expected value is what we call the e of x. The expected value is the mean. And guys, don't forget that when we talk about the mean number of successes in one interval, we do kind of prefer to use the Greek letter lambda, but you can still use mu. You'll notice that your calculator kind of defaults to mu, but lambda normally lets us know that there's an interval involved. Okay, so let me go ahead and point out that you are about to see a formula here. The calculator will actually do this formula for you. So again, it's more about learning the meaning of the symbols. Now, if you did not invest in a TI-8384 calculator or the Casio FX 9000s, then you're going to start to see that you're going to need to go the route of either the by hand route, which means learning a lot of formulas, or you're wanting to pick up on how to use the table. Again, I focus more on teaching with the TI-8384s, so just be aware of that. Okay. So the Poisson distribution, the random variable x, the probability of obtaining x successes in any particular interval is given by the probability that our random variable equals this amount, this value, is e to the power of a negative lambda times lambda to the power of x. All of that is divided by x factorial. Now, again, x is going to be our number of successes. E is already known to us. E is at 2.7182828828, blah, blah. Okay, that's like that pi. It's just E is Euler's number. And then we've got lambda there, which is the mean number of successes in the interval. And again, don't forget, like, again, this notation here, you can basically just also assume that it's basically our mu, okay? When calculating probabilities, in general, for pretty much almost any probability when we're in distributions, we're going to round to 4 decimal places. This kind of follows the convention that's actually established already in the tables. So for those of y'all that are trying to get away with this class with not having the most expensive calculator, it's possible, but you're going to have to kind of follow the table route. And that's why most things are going to be 4 decimal places. Okay. One thing I do want to point out, and this is just kind of a nice, simple, helpful, is make sure that when you calculate your mean, your lambda there, it's in the same unit of measure as the interval in the question. That's very important to keep those, the interval in question and your mean always using the same unit. So if one's talking about minutes and the other one's talking about hours, I need to convert them to where they're both in minutes or both in hours. Okay, so let's take a look at actual problem. So we're going to calculate the probability that our barber is feeling extra speedy one day and finishes 6 haircuts in 1 hour. Now, we're going to recall that he usually finishes one haircut every 15 minutes. Okay, so one of the things is we want to figure out kind of what exactly we're looking for. And in this problem, we can kind of see it says calculate the probability that he finishes 6 haircuts in 1 hour. So he's automatically asking us, find me the probability that x equals 6. And again, x itself, we are talking about haircuts. Now, finishes 6 haircuts in 1 hour. So we're talking about haircuts within an hour. And right away, we can kind of see that since we are talking about haircuts in an hour, not hours, sorry, hour, I have an interval. That hour that I'm talking about, that's an interval. Okay. Now, it does say that we need to kind of know a few other things. And this is where, like, I'm just pulling this all from the problem itself. So noticing that it does actually meet the conditions for Poisson here. It's namely independent of successes, and the mean number of successes per interval remain constant. Finishing one haircut is going to be independent of the other haircut. We also know that the average is usually a constant value of one haircut every 15 minutes. So that scenario can kind of basically model Poisson, because we're letting x be the number of haircuts finished in 1 hour. And again, I have something that's countable, number of haircuts. We're talking about countable items. And then 1 hour is that interval. That's how I kind of know we're using in the Poisson method versus remind yourself back for binomial, even though it was discrete. Binomial was success or failure and how many successes that you actually had. There was no time limit or any interval in which I was looking at on. Okay. Now we are looking for the probability that he finishes exactly 6 haircuts in 1 hour. So that's where our value for little x there is going to be x equals 6. We also have to understand that in the problem it talked about that he normally had haircuts. It took 15 minutes for one haircut. And that was minutes versus our interval here is in hours. So we kind of can say that the barber averages 4 haircuts per hour. And now that I've said 4 haircuts per hour, it's in the same unit as my interval of time that I'm using already. So therefore, my lambda there is going to be 4. We have the two values we need. The two values we need is basically I need to know what x is and I need to know what that lambda is. And now we can use our calculator. Okay, so the steps in the calculator that you want to do are going to be under starting with your distribution menu. So in your calculator, second vars, that takes us to that distribution menu. Again, you're going to be looking until you see Poisson PDF. Okay, you might have to scroll a little bit. Since it is near the bottom, you'll notice I kind of just when I went to that menu, so one more time, second vars, I went ahead and just hit up because I know it's at the bottom of the list. Most of your discrete stuff is going to be near the bottom. And then the continuous type stuff is going to be at the top. And we'll talk more about continuous in another chapter. Okay, we're going to type in what our x value was, and we're wanting to know what is the probability that he actually does 6 haircuts in 1 hour. We know that the lambda is that mean. So in this case here, the calculator does default to the mean. So make sure that for here, our mean was 4 because he's averaging 4 per hour. And we're wanting to know what's the probability that he actually does 6 per hour. Paste it in. Okay. For my TI 83 students, guys, you are not going to see that pop-up menu. It's literally going to come straight to this Poisson PDF, and you just need to type in your mean, comma, your what value of x you're looking for, And then once you hit enter, it's going to tell you your answer. And again, we're going to round it to 4 decimal places because that's kind of the standard with probability. And so I end up with 0.1042. Now, as I am looking at this here, I do notice that pretty much this is a decimal. If you're going to talk about it in terms of, say, a paper or something, I would probably switch it to a percentage. So we can see that the probability that he finishes 6 haircuts in 1 hour is about 10.42%, or also known as 0.1042. Now, when using the Poisson tables, precision is limited to the number of choices that are given on the table for like your average number of successes for any given interval. And yes, you guys do have access to these tables when you are taking a test. They weren't very well, like you were already given access to them for your Unit 2 test. But it is one of those that I would recommend using the calculator over the tables. Use the tables as a backup just in case. Okay, I am going to show you how to do it with the tables just so you have an idea of it, but be aware that it is a little bit of a lengthy process and you have to make sure you're reading the table correctly, just the same thing as if you were plugging it in the calculator. So suppose that a length of copper wiring averages 1 defect every 200 feet. What is the probability that a 300-foot stretch will have no defects? Okay, again, noticing probability that a 300-foot stretch will have no defects. So basically, we're looking for here a probability, which means my answer should be between 0 and 1, which we should have an idea there. Okay. But what I do know here is that basically the length of wiring averages 1 defect every 200 feet. So you have 1 defect per 200 feet. Now, guys, that's going to help us out basically right there, because that's kind of our average that we're using. But you'll notice this is using a measurement of 200 feet, and this is using a measurement of 300 feet. So those are our intervals in which we have to kind of play with a little bit. So each defect in the wire is considered to be independent of each other, and that the average number of defects in a given length of wire is going to be constant. So this scenario does meet our model for being Poisson because we were talking about it over an interval. And again, remember I said the interval doesn't have to be time. It can be any type, but I have like a set interval I'm looking at. Now we need to determine what lambda and x are. So first, let's go with lambda. If there's 1 defect on average every 200 feet, then we can expect 1.5 defects for a 300-foot stretch. Okay, so basically our lambda will be 1.5. And again, this is me creating that, making sure that they're on the same unit of measure. And that's where if you kind of look at it, it kind of helps you out. So think back, I wrote it as kind of a bit of a rate of change. So I'll go back 1 slide so you guys can see it's 1 defect per 200 feet. So 1 defect per 200 feet. And if I multiply this by 300 feet, you'll notice you get 1.5 defects on average. Okay, and this is just a good way to kind of see it. Again, this is kind of an average or a rate of change, and multiplying it by 300 feet, this means that we can get our units to be in the same interval, that basically it's 1.5 defects on average. Okay. So the other part is we're looking for the probability of seeing no defects. So that basically is x equals 0. So using the Poisson table to help us out here, we know that our lambda is 1.5, we know our x is 0, and so our answer is going to be 0.2231. And how I found it is by basically looking at my table. I look at my x's, again, here are my x's, here are my lambdas, and since I am seeing my x's and seeing my lambdas, I scroll down until I see the x I'm looking for. I scroll over until I see the lambda, and again, find where they cross each other, and that's going to be your probability there. Now, not too bad, but again, you have to make sure that you're looking at the right table, so make sure that you're looking at the Poisson table. For the calculator, the method is still going to be the same as what we were doing earlier. We are going to hit that distribution. We're also going to type in our 1.5 for our lambda and 0 for our x value, and you're going to get 0.2231. So we can say there's about a 22.31% chance of finding no defects in that 300 section foot of wire. Let's try another one. So again, you'll notice I'm looking for kind of some keywords here. I'm also noticing in these questions, I'm looking for what is it actually asking for. So a popular accounting office takes in an average of 3 new tax returns per day during tax season. What is the probability? Okay, automatically we know that we're looking for a probability here. So what is the probability that on a given day during tax season, the firm will take in just one new tax return? Okay, so I know off the bat here, again, we are kind of using Poisson because we're talking about tax returns during tax season, right? So that right there is kind of my interval that I'm looking for. We also know that it's going to be independent because, I mean, each tax return is not going to be dependent on the next one. One person's going to bring in a new tax return to a firm, cannot, is going to be independent of any other new tax return that comes in the next day. We also were told that the average per day is 3 new tax returns, so this is going to be constant. So our scenario here basically is what we call a Poisson distribution. So we're going to let X be the number of new tax returns, and in to the firm by one day. We are trying to obtain the new tax returns to be successes. So like if they come in at success. In the question it said we are looking for the probability that exactly one new return will come in one day. Okay, so X itself is being only 1, that's going to be X equals 1, and our lambda there was going to be 3. Now, do understand that if you are doing the by hand method, you are literally just plugging into the formula. Do be a little careful with the factorials. Okay, but once you plug it in, I mean, it pretty much plug it in and evaluate, and then you've got your answer. If you're doing the tables, again, the same thing. Look on the table. You need to make sure that you're looking at the table that has the probability that X equals X, because we were talking about exactly 1. You're going to look for the row that has X equals 1, look for the column that has your lambda being 3, and you'll see that they intersect at 0.1494. Okay. Again, if you're using the calculator, same kind of process here. We know that it's the probability that X equals X, which again, that is just saying that the probability that our random variable equals exactly this value. Okay. And normally in the problem, it is referring to exactly this value or finding about this item. It's not going to have any qualifying words that mean more or less. It's like just exactly that number. So again, you're going to hit that second vars, go to that beautiful distribution menu, scroll until you see Poisson PDF. Okay. There is a Poisson CDF. We'll get to that. Give me a second. But the PDF is, again, exactly to the point. My TI-84s, please, guys, remember that my TI-84s, this is what you see. For my TI-83s, you see this, but you have to enter in these numbers. Okay, so there is a little bit more for you to kind of remember if you have a TI-83, but it's still the same process. It's just the TI-84s have a menu that actually asks them, okay, remind them, what do you put here and here? Okay, once you put it in, you're going to just kind of evaluate it. Do remind yourself you are going to be rounding to 4 decimal places. This is kind of a constant on all of our probabilities. So basically from now on, 4 decimal places if it asks for a probability. So that 6 is going to round that up to a 4. So we get the probability that our variable x equals exactly 1 in this case here is going to be approximately 0.1494. Again, I'm going to put the 0 in the front just so I know that that is a decimal. You'll notice I have a squiggly equal. That means I did round that answer. Okay, so therefore the probability that this business gets one new tax return on any given day is really only a 14.94%. Let's try another one. Again, the more you actually practice these, the more you'll see them. But again, you're kind of looking for these keywords. So I'm trying to point out some of these keywords to help you guys out. Okay, so suppose in a rural area, the internet connection at Olivia's house goes out on average 0.9 times every hour. 0.9 times every hour. We have kind of an interval there. Now, if she plans to be connected to the internet for 3 hours in one afternoon, what is the probability that she will stay connected the entire time? So what is the probability that she's connected for 3 hours in one afternoon? Okay. Now, in our case here, remember, it's 0.9 times every hour. So understand that as we are kind of looking at this and making sure that we have everything, we know that we are looking for the probability of something. So we have the probability that our x equals some number. Okay? But remind yourself that our average is on average, the internet goes out. Okay? So this is where, what exactly is x? Well, x is the number of times that we disconnect. Okay? And this is, like I said, this is kind of where you're kind of thinking your way through. We know that we're looking for the probability that x equals something, but what is x? This is where our 5.1 knowledge comes in. What is x? What exactly are we looking for? Well, we're asking what is the probability that she stays connected the whole time? So x is basically the like what we're not getting internet. When are we not getting internet? Okay, so we need to consider that a disconnection is a success for this problem. I know that sounds a little strange, but we're saying that we stay connected the whole time. So it makes it a little bit easier to solve the problem this way. So with this in mind, we note that a disconnection is going to be independent on any other disconnection. The average rate of disconnection per hour is constant. So we do meet the Poisson model. So X is going to be the number of internet disconnects in any given 3-hour period. Now, why did I switch to 3-hour period? Well, because that's what I'm asking for on that interval. Now, we know that we are looking for the probability that no successes occur, so no disconnections in that 3-hour period. So we know X is going to be 0. But what about lambda? What about our average? Well, the connections average 0.9 disconnects each hour. So for a 3-hour period, again, remember I said they have to have like the same unit of measure there. We are literally taking 0.9 divided by 1, because 1 hour, right, times 3, which gives us 2.7. And that's how you're kind of working your way through finding these words. Again, I'm just going to use the calculator to help me out here. I know that I'm looking for exactly 0, meaning no disconnects whatsoever. So we have the probability that x equals 0 using our Poisson distribution with our mean being 2.7, our x value being 0, which is going to give us about a 0.0672. Okay, and basically we can say that the probability of staying connected for all 3 hours is actually 6.72%. Now, all of those we've done so far have been the words exactly this number. Okay, But what if it doesn't have that word? So what if I use something like a fast food restaurant averages one incorrect order every 3 hours? Okay. What is the probability that the restaurant will get no more than 3 orders wrong on any given day between 5 and 11 p.m.? Now, we're going to assume that the number of incorrect orders follows our Poisson distribution. There can be a little bit with orders in restaurant, but we're going to assume that these are all independent of each other. But the key word there was no more than. When we say no more than 3 orders wrong, this allows us to use not just an exact number for probability, we are looking at a cumulative probability. Okay? So there is a difference in the commands when we use these ones. So Poisson PDF is for a single, like you're looking for what's the probability of this happening. But when I use words like no more than, less than, greater than, then we're using a tweak on it, and we're going to have to use the CDF because we're talking about cumulative words, stuff that builds. Now, be aware that the only one in the calculator is this one with the CDF. So it's only a less than or equal to symbol, which, ladies and gentlemen, you are going to have to do a bit of thinking of how we adjust these symbols to help us work out. So starting us off there, we basically will consider the wrong order as a success. So X be the number of incorrect orders that occur between 5 and 11 p.m. on any given day. Now we know that we are looking for the probability of getting no more than 3, which means I can get 3 and less, but nothing bigger than it. So we're looking at the probability that X is less than or equal to 3. Now to calculate lambda, we need to calculate the average number of incorrect orders on a 6-hour period. How do I know it's a 6-hour period? Well, they gave me from 5 to 11, which is 6 hours. But the average they gave us was a 3-hour period. So again, those intervals have to match. So it's pretty nice because 3 times 2 is going to be a 6-hour period there. So I can just take the lambda that they gave me and multiply it by 2, and I should be good. And we're going to find basically the probability that X equals 0, 1, 2, or 3. And this is where the cumulative comes in. Now, remind yourself that the probability that X is less than or equal to 3 is what I'm looking for. We have a button in the calculator that does this. Now, if you're doing this by hand, remember that crazy formula. The formula I had did not work for the less than or equal to. In order for the formula to work, you basically have to break it down and show it as the probability of X equals 0, 1, 2, and 3, and add those all up, getting your answer. Okay? And the same thing is going to have to hold true for the tables. You literally have to go to the probability that X equals X on the tables, find your correct lambda, find your correct X, and you have to do the X's of 0, 1, 2, 3, and add those all up again. So it's possible to get that same answer. However, guys, you're going to create yourself a heck of a lot more work if you're doing this by hand or using the tables, because we don't have a table for the probability that X is less than or equal to X. We have a table that's X equal to X. So in this case here, the calculator does work really nicely, okay? And just like what we learned earlier, the calculator can calculate binomial probabilities for cumulatives. It can calculate cumulative Poisson probability as well. So this way we don't actually have to find each of these individual probabilities. We can just put it in one time. We don't have to do each one individually and add them together. So again, still going in that calculator in that same area. Okay. And second bars going to the distribution screen. Again, noticing here is where that Poisson CDF is. You'll notice that it looks pretty much identical to what we were looking at earlier. So you're still typing in your mean. You're typing in what your X value is. For those that have a TI-83, you're still going to be saying click the Poisson CDF and then your mean, comma, your x value and then close the parentheses and enter, and you get that same answer of 0.8571. Now again, you can go the longer route and do it by hand or with the tables, but again, not necessarily. It will be a little bit longer, but the calculator will do this for you. Okay, and again, just all you have to do is plug it in, and it's real nice and neat. So in this problem in particular, we know that the fast food restaurant has about an 85.71% chance of getting no more than 3 orders wrong on any given day between 5 and 11 p.m. So let's take a look at this problem here. A math professor averages grading 20 exams per hour. What is the probability that she grades more than 35 of her 60 statistics exams during her uninterrupted hour and a half between classes? And we're going to assume that the number of exams graded follows a Poisson distribution. And we're kind of given a hint that it's Poisson because they give us intervals, right? So what is the probability? That's my first keyword. So I know I'm looking for a probability that she grades more than 35 of her 60 statistics exams during her uninterrupted of an hour and a half between classes. Now, they gave us that the average is 20 exams per hour. So those are a lot of keywords there that I pointed out. And those keywords are really what's going to help me out tremendously as I work my way through this problem. I'm going to start with the probability. So the probability that she's grading exams, and keyword there was more than 35. Okay. Now, here's the deal though. Remember when I said the calculator only does the probability that x is less than or equal to x. Nowhere did I say it does more than. Okay? So we have to think about this a little bit. So to help us think here, we know that x is defining a success of that she's graded an exam. Okay? Now, letting x be the number of exams graded in 1.5 hours, and we want to find the probability that more than 35 successes occur. This is where that probability is basically x is greater than 35. However, again, the calculator does not have a greater than symbol. It only has a less than or equal to. So in this case here, the complement rule is actually in our favor here. So we know that 1 minus the probability that x is less than or equal to 35 will be the complement. So that must be the probability of x is greater than 35. And if I have 1 minus the probability of x is less than or equal to 35, we can now put it in the calculator. Now, before we can put it in the calculator, we do need to know what our lambda is. We know x is 35, so we're good there. But we do need to know lambda. And we know that she averages in 1 hour 20 exams. But remind yourself that we are actually looking at not 1 hour, but an hour and a half. So if the average for 1.5 is basically going to be 20 times 1.5, so the timing gets right, which will be 30. Okay, and that will allow me to figure out everything I need for the Poisson formula and table. But again, it's very time consuming to do those, whereas we can just use the calculator to help us out. And basically, we're just going to do 1 minus the probability that x is less than or equal to 35. And I'll show you on a screenshot here that what that is. But this is pretty much it's 1 minus Poisson CDF, putting in 30, because remember, this is that lambda, comma, x. Okay, and we got 0.1574, which is, this is what it should look like in the calculator. So basically what this tells me is that the math professor has a 15.75% chance of getting more than 35 statistics exams graded between her classes. Okay, so again, remember our biggest part is just finding these keywords. So a typist averages 4 typographical errors per paragraph. Per paragraph right there, that's an interval, guys. If he is typing a 5-paragraph document, what is the probability that he will have fewer than 10 mistakes? Okay, looking for some keywords here to make sure that we got our keywords. averages 4 errors per paragraph. That's going to probably help me out with my lambda there. We're asking what is the probability that he makes fewer than 10 mistakes, okay? But they did say if he's typing a 5-paragraph document, which is that's the interval for what we're looking at. Now, fewer than might confuse you a little bit, but basically the probability of, we'll say X is making a mistake on the document, right? Because that's kind of what, fewer than this many mistakes, so X is going to be the number of mistakes you make in a paragraph in particular, because we are talking about in terms of a paragraph itself. Okay, fewer than 10. Fewer than 10. Fewer than is the same thing as saying less than. Okay, again, guys, do remember this is not in the calculator. The calculator only does the probability that X equals some number, or the probability that X is less than or equal to X. Which this is where it involves us doing a little bit of tweaking, because this is a discrete probability. So we're defining a success as making a mistake. So X is the number of mistakes made in the document. Now, if the typist averages 4 mistakes per paragraph and his average is for 5 paragraphs, 4 mistakes per paragraph times 5 paragraphs means we're looking at 20 mistakes as our average for the 5 paragraphs. So our lambda there is 20. We are looking for the probability that's fewer than 10 mistakes, which is at less than 10. But again, we need to rewrite it. And guys, do remember that if it's less than 10, the first number that's less than 10, because we're discrete here, is 9. So we're really actually looking for the probability that our number of mistakes is less than or equal to 9. And now we can use our calculator. So again, plugging it in the calculator, using that Poisson CDF, so 20, 9, and we're going to get 0.005. Again, guys, do remember that you are using the Poisson CDF at this point, and that you are going to want to make sure to type in your numbers for my TI-83s. You really do, like, you don't even get this part here. You just have to remember that this is lambda and this is X. Okay. Thus, basically, that tells us that we have a 0.50% probability. Guys, remember, don't convert back and forth unless you're kind of writing a paper. If you're writing a paper, then it's better to use a percentage. So this is better for papers. If you are just writing in your homework, guys, this is the one for the homework that you want to use. Okay. I did see people trying to make conversions and things like that, and it's best to just leave it be. When in doubt, don't convert anything unless it specifically asks for that. Okay, and that is Poisson distribution.